Invisible threads of magnetism weave the cosmos together and then violently snap. These magnetic bridges represent one of the greatest unsolved puzzles in modern astronomy. And by the end of this, you will understand the hidden forces that build and shatter entire galaxies. What triggers these cosmic filaments to suddenly break apart? And how do galaxies rewire themselves in the aftermath? What does it feel like to live in a universe stitched together by such powerful, invisible strings? These immense magnetic fields are born within the chaos of a young galaxy. Picture a vast, swirling disk of superheated gas, a churning sea of charged particles. Within this chaos lies a natural power generator, a cosmic engine known as a dynamo. It works much like the dynamo on a bicycle, where spinning motion creates an electrical current, but here the scale is almost beyond comprehension. The entire galaxy itself is the engine, its slow, majestic rotation spinning that ionized gas and stretching the faintest magnetic whispers into powerful, organized fields. Those initial seeds of magnetism are thought to be ancient relics, perhaps imprinted in the fabric of the universe during the Big Bang itself. Over billions of years, the galactic dynamo amplifies them, transforming a cosmic murmur into a defining roar. This process, called magnetohydrodynamics, is where charged particles become trapped, spiraling along these emerging field lines and steadily feeding them energy. It is not a gentle process. Turbulence from exploding stars, the sheer forces of galactic rotation, and even violent collisions with other galaxies all stir the pot, influencing the final shape and strength of the magnetic architecture. The magnetic field woven through our own Milky Way likely carries the scars and signatures of ancient mergers, a fossilized record of past cosmic violence. How does the origin of these fields determine their ultimate fate? A field born from turbulence may be inherently more unstable, its connections more fragile, setting the stage for the dramatic breaking points we observe across the universe. These colossal magnetic bridges begin as galactic neighbors drift too close. Picture two immense islands of stars, each with its own powerful magnetic field, sailing through the void on a slow-motion collision course. Their gravitational pull stretches the very space between them, creating immense tidal forces. As they pass, these forces pull and warp their magnetic fields, much like two powerful magnets would influence each other in a cosmic dance. The fields do not simply bounce off. Instead, they become entangled, connecting the two galaxies with invisible threads. Galactic winds, vast outflows of charged particles blown by supernova and black holes, then pour out, inflating these entangled fields and stretching them into vast, filamentary bridges that span the incredible emptiness. This process is supercharged by what astronomers call ram pressure. As a galaxy moves at tremendous speeds through the thin, superheated gas that fills galaxy clusters, this intracluster medium acts like a powerful cosmic wind, stripping material away. But it does not just strip gas, it also peels the galaxy's magnetic field away, pulling it out into long, streaming tails that can easily connect to a neighbor. Observations from powerful radio telescopes like the Very Large Array have provided stunning evidence. They detect a specific type of light called synchrotron radiation, a telltale glow emitted by electrons spiraling at near light speed along these magnetic pathways. In the Virgo cluster, a dense gathering of galaxies relatively close to us, we see these bridges clearly. They act as cosmic highways, as cosmologist Dr. Liam Chen describes them, channeling vast rivers of gas and cosmic rays from one galaxy to another. This transferred material is the raw fuel for creation, capable of igniting new stellar nurseries and feeding the voracious black holes at galactic centers. For such a bridge to stabilize and endure, the conditions must be just right. The galaxies need sufficient mass to generate strong gravitational and magnetic forces. Their relative velocity cannot be so high that it shreds the connection instantly, and the density of the surrounding intergalactic medium must provide just enough resistance to shape the bridge without tearing it apart. These stable bridges become vital parts of the cosmic web, but their stability is only temporary, setting the stage for the immense forces that will one day tear them apart. That stability is a fragile illusion. A magnetic bridge is like a cosmic rubber band stretched taut between two galaxies, and like any overstretched band, it can snap without warning. The forces that cause these titanic structures to rupture are as powerful as those that built them. Galactic collisions are one of the main culprits. When two galaxies finally merge, their chaotic gravitational dance creates immense shear forces, pulling the magnetic fields in opposite directions and ripping them apart. Even a galaxy spinning too rapidly can fling its own magnetic field lines outward until they simply break. Then there are the violent astrophysical events from within. A supernova explosion can send a devastating shockwave through the bridge, while an outburst from an active galactic nucleus, a supermassive black hole feasting on matter, can blast the entire structure with unimaginable energy. Astrophysicist Dr. Maria Kowalski explains that the snap is not just a rupture, it is a transformation. It releases a flood of pent-up magnetic energy that can heat surrounding gas to millions of degrees, accelerate particles to near light speed, and paradoxically, even trigger the birth of new stars. The key mechanism at work here is called magnetic reconnection. This is a process where the stressed magnetic field lines break and then reconnect in a new, lower energy configuration. In that moment of reconnection, vast amounts of magnetic energy are converted directly into intense heat and violent kinetic motion, like a cosmic short circuit. We see the evidence in places like the antennae galaxies, two spiral systems currently colliding. Radio telescopes reveal snapped magnetic bridges between their cores, visible as fragmented tendrils of radio emission. So how does this explosive energy dissipation reshape the galactic environment? The sudden release heats vast clouds of gas, preventing them from cooling and collapsing into stars, or conversely, it can compress other gas clouds so violently that new star formation ignites. It accelerates cosmic rays, creating a haze of high-energy particles. The snap fundamentally alters the gas dynamics of the entire region, forcing the galaxies to find new ways to interact. But what happens to the broken pieces of these magnetic fields? They do not simply vanish. The broken ends of a magnetic field do not drift aimlessly. They are alive with pent-up energy, desperately seeking a new, more stable path. This is the moment of cosmic rewiring, a fundamental process that rebuilds galactic connections from the wreckage of a snap. The primary force behind this reconstruction is magnetic reconnection, the same phenomenon that caused the rupture. When the stressed field lines break, they do not simply vanish, they violently rearrange themselves into a new, lower energy configuration. The broken ends, still infused with powerful magnetism, snake outward through the surrounding plasma, searching for other magnetic structures to latch onto. They might realign with weaker fields from the original galaxy, form closed loops that connect to entirely different regions, or even link up with the magnetic filaments of a passing neighbor. Plasma physicist Dr. Ben Carter describes this as nature's way of optimizing cosmic circuits, ensuring that magnetic energy continues to influence galactic evolution long after the initial disruption has passed. This rewiring is not a gentle process. It is driven by plasma instabilities and cascading turbulence, where the energy from the broken bridge dissipates in a chaotic storm, only to reorganize into new, coherent structures. We can see this in action through sophisticated computer simulations of galaxy mergers. As two galaxies tear each other apart, their gravitational forces create long streams of stars and gas called tidal tails. The simulations show that the rewired magnetic fields often realign perfectly along these tails, tracing them like glowing wires on a circuit board. A stunning real-world example exists in the mice galaxies, a pair of colliding spirals. Astronomers have observed that rewired magnetism is now channeling vast flows of gas into the tidal bridges stretching between them. This redirected material is igniting star formation in areas that were once quiet and empty, building new suns from the aftermath of cosmic chaos. So what decides where these new magnetic pathways form? The final configuration is not random. It is dictated by the galaxy's own spin, which can twist the fields into new alignments. It is shaped by the subtle influence of external magnetic fields permeating the intergalactic void. Most crucially, it depends on the density and distribution of ionized gas, the conductive fuel that the magnetic fields need to take root. This entire rewiring process showcases the profoundly adaptive nature of cosmic magnetism, a force that refuses to be silenced. But how does this newly rewired magnetic circuitry ultimately change the fate of a galaxy, altering its very ecosystem from the inside out? A magnetic snap can redefine the very heart of a galactic ecosystem. Think of these magnetic bridges as cosmic arteries, and the gas they carry as the lifeblood of star formation. When one of these colossal structures suddenly tears apart, it triggers a chain reaction that either breathes new life into stellar nurseries or leaves them to wither. The outcome hinges on how the snap and the subsequent rewiring alter the three essential ingredients for making stars: gas compression, turbulence, and the final collapse of a molecular cloud. An intact, stable bridge acts like a focused delivery system, channeling vast rivers of cold gas directly into a galaxy's core. This concentrated influx can ignite a starburst, a ferocious period where thousands of stars are born at once. But when the bridge snaps, that orderly flow shatters. The released energy can violently disperse the gas, preventing it from ever cooling and collapsing, effectively putting star formation on hold across entire regions. Yet, in a stunning paradox, that same explosive energy can also squeeze other gas clouds with immense force, triggering a different wave of star birth in entirely new locations. Astrophysicist Dr. Anya Sharma, who studies these stellar genesis events, describes it this way: magnetic fields provide the scaffolding for cosmic nurseries. Their reconfiguration can either nurture or stifle stellar genesis. We see this dramatic interplay clearly in the Whirlpool galaxy. There, powerful magnetic bridges correlate perfectly with its most intense star-forming regions, the field lines visibly guiding and compressing inflows of gas. But in systems that have recently undergone a magnetic disruption, the story changes. The rewired fields create strange new pockets of high-density gas, leading to the sudden, brilliant appearance of massive star clusters in places that were once dark and quiet. Conversely, other areas of the same galaxy can be left gas-poor and dormant, their potential for new suns effectively stolen. This magnetic influence reaches far beyond a few star clusters. The rate of star formation directly sculpts a galaxy's long-term evolution. It determines its morphology, whether it remains a grand spiral or settles into a smooth, elliptical shape. It sets the galaxy's metallicity, the abundance of heavy elements forged in stellar furnaces that are essential for building planets and, ultimately, life. A galaxy whose magnetic arteries are constantly snapping and rewiring will have a chaotic and uneven history of star birth, which profoundly affects its chances of ever hosting a habitable world. This leads us to a deeper, more shadowy question. What invisible hand is guiding the gravity that holds these entire magnetic ecosystems together? The answer may lie with the most elusive substance in the universe. Dark matter is the silent architect of the cosmic stage. This invisible substance, which makes up the vast majority of a galaxy's mass, does not feel magnetism itself, yet its immense gravitational presence dictates the entire play. Its pull shapes the grand distribution of galaxies and the rivers of hot gas between them, which in turn determines precisely where magnetic bridges can form and how much strain they must endure. Cosmologist Dr. Samuel Jones explains that dark matter acts as the stage director for cosmic magnetism, setting the scenes where these dramatic rewirings unfold. Imagine a dense knot of dark matter, a massive halo surrounding a galaxy cluster. This concentrated gravity intensifies every interaction. When galaxies pass each other in such a crowded region, the dark matter's pull amplifies the tidal forces, stretching magnetic bridges to their absolute limits and making them far more prone to a catastrophic snap. Sophisticated computer simulations reveal this clearly. In galaxy clusters with exceptionally high dark matter density, the magnetic bridges that form are often more extensive, spanning greater distances, but they are also significantly more fragile, living on a razor's edge. A stunning real-world example is the Bullet Cluster, a cosmic collision of epic proportions. Observations show that the dark matter, mapped through its gravitational lensing effects, is perfectly aligned with regions of highly distorted and fragmented magnetic fields between the colliding galaxies. This is the invisible hand, warping the very fabric of space and twisting the magnetic structures within it. But could dark matter be more than just a gravitational director? Some speculative theories propose that certain hypothetical dark matter particles, like actions, might themselves generate incredibly subtle magnetic fields. These could contribute to the primordial seeds that galactic dynamos later amplify, though this remains a tantalizing frontier of research. By understanding this profound interplay between the seen and the unseen, we grasp that the fate of a magnetic bridge is written not just by the glowing gas we can observe, but by the dark gravitational wells that we cannot. To truly witness this cosmic drama, we need eyes that can peer into the magnetic heart of the universe itself. Our window into this invisible architecture is built from light we cannot even see. Astronomers peer into the magnetic heart of the cosmos using radio waves, a form of light invisible to our eyes but rich with information. Massive radio telescopes like the Square Kilometre Array, a network of dishes spanning continents, and the Atacama Large Millimeter Array, perched high in the Chilean desert, act as our cosmic ears. They listen for two key signatures. The first is synchrotron radiation, that distinct glow emitted by electrons spiraling at nearly the speed of light along magnetic pathways. Its intensity reveals the strength of the field. The second is Faraday rotation, a subtle effect where the magnetic field twists the polarization of radio waves as they travel through space. By measuring this twist, scientists can deduce the field's direction and density. It is like having a compass that points not north, but directly into the magnetic fabric of the universe. Radio astronomer Dr. Rachel Lee describes each observation as developing a new sense, allowing us to see the magnetic skeleton of the universe. To fill in the details, astronomers use other ingenious techniques. Zeeman splitting detects magnetic fields within dense gas clouds by looking for tiny shifts in the spectral lines of atoms, a split caused by magnetism's influence. Another method maps the polarization of light emitted by cosmic dust grains. These tiny particles align themselves with magnetic field lines like countless microscopic compass needles, and the light they emit becomes polarized, tracing the field's structure with incredible precision. A stunning success of these combined tools came from studies of the Coma Cluster, a dense swarm of galaxies. By overlaying data from X-ray observatories, which see the hot plasma, with radio telescope maps, astronomers clearly saw magnetic bridges channeling that very plasma between galaxies. Yet observing these cosmic filaments is a monumental challenge. The signals are incredibly faint, drowned out by noise from our own galaxy and the subtle hum of the universe itself. Detecting a magnetic field in another galaxy is like trying to hear a whisper in a hurricane. This relentless push against the limits of our technology is what drives the next generation of observatories, missions designed to finally listen to the universe's quietest magnetic conversations. These cosmic laboratories exist inside the world's most powerful supercomputers, where equations become dynamic, virtual universes. To understand the life cycle of a magnetic bridge, scientists feed the laws of physics into complex magneto-hydrodynamic codes. These are not simple animations, they are mathematical engines that calculate how every parcel of ionized gas moves, how it responds to gravity and pressure, and most importantly, how its motion twists and amplifies magnetic fields. The code must account for the explosive violence of supernova, the relentless pull of dark matter halos, and even the subtle stretching of the cosmos itself. Astrophysicist Dr. Kenji Tanaka describes simulations as our cosmic laboratories, letting us replay galactic interactions millions of times to isolate key variables. We can watch a magnetic bridge form, snap, and rewire over billions of virtual years, and then rewind the tape to see what would have happened if one galaxy had been spinning just a little bit faster. Pioneering projects like the Illustris TNG simulation have given us a grand cosmological view, showing how magnetic fields grow and evolve in lockstep with tens of thousands of simulated galaxies. Meanwhile, the ENSO project focuses on the fine details, capturing the violent, microscopic physics of magnetic reconnection events with stunning clarity. These virtual experiments have made startling predictions. Simulations of the Magellanic Clouds, two small galaxies orbiting our own Milky Way, suggest they are connected to us by faint magnetic bridges that may be on the verge of snapping due to the Milky Way's immense tidal gravity. This impending rupture could alter the flow of gas into our galaxy, changing the recipe for future stars. The insights run even deeper. Models reveal that these magnetic structures act as cosmic flywheels, regulating a galaxy's spin by transferring angular momentum away from the core. They can funnel gas directly into the maw of a supermassive black hole, turning a quiet beast into an active, shining nucleus. They might even be the original source of all magnetism, planting the primordial seeds in the first protogalaxies that would one day be amplified into the powerful fields we see today. Yet for all their power, these simulations are not perfect. There are still frustrating discrepancies between what the models predict and what our telescopes actually see in the night sky. The simulated magnetic fields are sometimes too strong or too weak, or they snap at the wrong moment. These gaps are not failures, they are clues, pointing toward physics we have not yet discovered or processes we do not fully understand. They drive the relentless need for more refined theories and more powerful computers, pushing us toward a more complete picture of our magnetic cosmos. For all we have uncovered, the true nature of magnetic bridges remains one of astronomy's most compelling frontiers. Researchers are still grappling with fundamental unknowns, starting with the very strength of these fields. How did cosmic magnetism achieve its current power? We know galactic dynamos amplify weak seeds, but the origin and initial strength of those seeds is a deep mystery. Were they truly imprinted at the birth of the universe, or did some later process plant them? Another pressing question involves turbulence. This chaotic motion is essential for building the fields, but it might also be the very thing that makes them so fragile. The exact role turbulence plays in determining a bridge's stability, whether it acts as a builder or a destroyer, is not yet clear. Perhaps the most profound unknown is how far back in time these structures go. Do magnetic bridges exist in the infant universe, weaving between the first primitive galaxies? Upcoming missions are designed to find out. The James Webb Space Telescope, with its infrared eyes, will probe the magnetic environments of high-redshift galaxies, looking for the faint signatures of these fields in the cosmic dawn. Meanwhile, the Cherenkov Telescope Array will search for very high-energy gamma rays, which could be the telltale sign of cosmic rays accelerated by snapping magnetic bridges. Theoretical physicist Dr. Olivia Grant captures the spirit of this search, noting that every answer we find opens new doors. For instance, could magnetic bridges influence large-scale cosmic flows like the dark flow anomaly, a mysterious, uniform motion of galaxy clusters that current physics cannot fully explain? Other puzzles are more technical but equally profound. Scientists are still trying to understand the efficiency of magnetic reconnection in the near vacuum of intergalactic space, a low-density environment where the rules of plasma physics might operate differently. There is also the tantalizing possibility that these bridges are the natural accelerators for ultra-high-energy cosmic rays, the most energetic particles ever detected, whose origins have baffled physicists for decades. The quest to solve these mysteries is being supercharged by new tools. Artificial intelligence and machine learning are now scanning the skies, analyzing vast datasets from radio telescopes to identify subtle magnetic patterns that the human eye would miss. These algorithms could uncover bridges in entirely unexpected places, revealing a cosmic web of magnetism far more extensive and intricate than we ever imagined. As we stand on the brink of these discoveries, the enduring enigma of magnetic bridges invites us to completely rethink our place in a cosmos stitched together by invisible, dynamic strings. Our exploration has unveiled a cosmos threaded with invisible, living filaments. These magnetic bridges are not passive decorations. They are fundamental architects, actively forging and dismantling the grand structures we see. Their entire life cycle, from a faint whisper amplified in a galactic dynamo to a catastrophic snap and a brilliant rewiring, directly sculpts the destiny of galaxies. They govern the birth of stars, guide the flow of cosmic material, and dance to the gravitational tune of dark matter. Through the combined power of advanced observation and sophisticated simulation, we have learned to read this magnetic language, to see the universe not just as a collection of isolated islands, but as a single, interconnected web. Yet for every answer, a deeper question emerges, driving the next wave of telescopes and supercomputers to probe further. The cosmos is indeed within us. We are made of star stuff, elements forged in stellar furnaces whose very creation was guided by these magnetic fields. We are, in a very real sense, children of the cosmic magnetism that binds the universe together. The next time you gaze at the night sky, remember the hidden tapestry above, a dynamic fabric of force that is constantly tearing and mending itself. We invite you to share your wonder and your questions about these cosmic strings in the comments below. For more journeys into the heart of space's greatest mysteries, be sure to subscribe.